So the last speaker of our morning session is George Benke from Georgetown University, who will be talking on phase arrays and some problems in harmonic analysis.
Thank you. I'd like to thank John and Norbert Lunar Center for inviting me to this talk. Also, given the time here, I feel very confident with my view graphs, since it's right about this time yesterday that the projector well, yeah, but I think we can replace that faster. And not only that, I have a hard copy I can write on the board. So I want to talk about two extremal problems. And an extremal problem, roughly speaking, from my perspective, is some kind of a problem which can be phrased as how close can we get to some situation which is actually impossible to get to, but we would like to get close to it. And so the two problems, one of them has received very little attention really from the mathematical community, but a tremendous amount of attention from the engineers. And the other extreme problem, I think, is sort of the reverse situation. So let me state the first problem. This is the one I'm primarily interested in here. And roughly speaking, the question is we have n integers which we would like to distribute over an interval of integers that is p times as long. And we simply consider the trigonometric polynomial with those frequencies given by those integers. And then the question becomes, how can we make this thing look as much like a delta function as possible? Well, let's see, a delta function in the
George, what restrictions are completely arbitrary?
Well, right now here, Q, I mean, we have integers here, so we have here a periodic function, 2π periodic function, and so we're interested in a period, basically. What's this look like in a period? So, a somewhat more precise formulation mathematically than just saying looks like a delta function, we could phrase in this way. So we're interested here in our polynomial. And by a delta function in the context of polynomials, we're going to take this expression here. And this is kind of our model, our polynomial model, so to speak, of a delta function. And of course, it's basically looks very much like a Dirichlet kernel. If the P here were inside, it would be exactly a Dirichlet kernel. So it's very close, and we'll see why I chose this particular formulation of my sort of polynomial version of the delta function. So this is the problem, and before giving one solution to this problem, I'd like to give the background, since we're not all antenna and radar engineers in the audience. I'd like to sort of explain the relationship to the problem of arrays. So a phase array or phase array antenna, if you want to use that terminology, is a collection of sensors here, which senses some sort of a field. So let's say we have a propagating field propagating in the direction of some vector n. These sensors here pick it up, and then the outputs from these sensors are weighted by some weight functions. And so we form a linear combination here, some combination of time. Now, if we have a propagating plane wave here with a radiant frequency omega propagating with the direction vector and some velocity here, and simply form this linear combination in this way, when we make this substitution into here, the time-dependent part factors out. And so what the output of the antenna sees is basically an oscillation here, radiant frequency omega, multiplied by some factor here, which is a function of n, a function of the direction of arrival. And so what that means is that means our antenna here is potentially more sensitive in some directions than others, to the incoming wave. And so this quantity over here might be called the beam pattern of the antenna, and that's really what we're interested in. And in particular, the idea is to make this thing here have a very large peak in one direction and be insensitive to other directions. So this is the electronic equivalent of taking a dish and pointing it mechanically. Well, let's see. Notice if we pick a particular direction here, n sub 0, by simply choosing weights, which are these numbers here, this quantity here achieves a maximum in that particular direction, which is n. And so by choosing coefficients in this particular way is basically how we steer the antenna and point it in a certain direction of interest. Now, the simplest case to look at in terms of the array geometry, and something that's been studied fairly extensively, is what are called line arrays. And so the idea here is to simply put our sensors on a line. So here's the equation of a line, and here's a direction vector for it. And it turns out to be convenient to assume that the length of our direction vector is half the wavelength of the propagating plane wave that's coming in. So if we do that, and if we also set these things to the integers here, then what we're really doing is we are really placing our sensors on a line with spacings that are multiples of half wavelengths of the incoming radiation. And if you do that and make the substitution from the previous slide, there's a dot product involved and so on. So these cosines come from that. The other terms in the dot product factor out in front, so we have this. Now the thing we're primarily interested in is the magnitude of this function here. And so this phase term here is really not of that much interest. And so the whole action is really over here in this expression. Now, in here, if we make this very simple change of variables, let u equal cosine theta over 2, then in the end, what the whole thing really boils down to, and since the fact that theta represents an angle here, we're not interested, so that limits terms running between plus and minus a half in here. And what that boils down to in the end is that, so this expression here is then really can be reduced to saying we'd like to study polynomials like this over one period, where the xk's are integers which correspond to how we're placing our sensors on this lambda over 2 lattice. Okay, so this is where this extremal problem came from that I sort of stated at the very beginning. This is why we're interested in looking at these polynomials to begin with. So if you look, so let's look at the simplest conceivable case. So let's just place our sensors at consecutive intervals here. And then, of course, what we get is the Dirichlet kernel, having a familiar picture of it. And so what we get here is we get this big peak at the middle, which engineers refer to as the main lobe of the antenna pattern. And the things outside here referred to as the side lobes. And again, in a certain sense, is this we would like to look as much like a delta function as possible. It would be nice to have this be very narrow, and to have these things here going all together, and then we have a really good antenna. It picks up perfectly in one direction, picks up nothing from any other direction, and so that's kind of the ideal. If we take our sensors and we spread them out, so suppose you have a spacing of p, but still an arithmetic progression, then we get an expression like this. So all we're doing here is reducing the period by a factor of p, And there are two things that happen here, one of which is good and the other is bad. The good part is that the central peak here, of course, has gotten more narrow, so we have much better resolution than before. The bad part is that we have these extra peaks showing up here, and these are referred to as grating lobes, and they represent an ambiguity in direction. So potentially, you might get a large output from your antenna that you steered in a certain direction, corresponding to the main peak, but really the radiation came from something else, and so you get a false reading. So what you like to do is you would like to basically suppress these peaks over here. Now, since this is a polynomial here, the L2 norm is the square root of n, so we have these energy considerations. And because these peaks are going up to n and the L2 norm, you square the vertical coordinate, there's actually a fair amount of energy in these peaks, these other two peaks, which means if you somehow manage to squash them down, the energy has to go into the side lobes down in here. So you're going to pay a price by pushing down peaks in terms of the side lobes over here. The side lobes over here, I mean, these of course are a direct result of the precise arithmetic of the placing of these sensors over here. So a way of suppressing these extra grating lobes over here would be to break up the regular arithmetic spacing of things. One of the ways this was done first was basically by just doing a monotonically increasing width between the spacings. And these things were referred to as tapered arrays. And you can analyze tapered arrays pretty well by using stationary phase methods and the like, because you can write down a nice formula for the distance of the gaps increases monotonically and the like. And when you're dealing with taper arrays, though, if you look at it, what happens as you get, let's call it a more drastic taper, the far out grating lobes, if there are more of them here, they will drop faster than the ones that are closer in. And eventually, when you get the close ones in, to be reasonable, the outside ones, things are pretty wild out there. And you get an array pattern which doesn't have a nice uniform structure in terms of the side lobes. So tapered arrays have their drawbacks here. The next thing was, well, instead of doing that, how about some sort of random distribution of things? And so there's an extensive literature on so-called random arrays. And if you look at the random case, you can do some simple computations here, and you can say, well, so suppose we take our sensors to be uniformly distributed over our interval here. By the way, the interval from 0 out to here is referred to as the aperture of the antenna. So if we distribute these at random and calculate the expectation, one gets this expression over here. Now, if you recall, this basically was the expression I had at the beginning that I said was going to be my model of the delta function. So in a sense, this is kind of the generic situation we have here with no particular prejudice about arithmetic structure or anything like that, and that's sort of why we use this as a model. You can also calculate the variance here, and the variance actually tells us something pretty interesting, which I'll show in terms of a picture here later. Let's see. Just to bring some technology into my presentation, here's an actual computer-generated. Oh, sorry. Well, this is not that informative anyway. It's just a graph of the Georgetown kernel with 40 elements in it. Again, here's the Dirichlet kernel where we've increased the spacing by 3, and we see those two grating lobes over there, 40 elements. Now, if we take the random case, so basically the formula that I just put up there, basically we get this. So this is 40 elements spread over an aperture, basically which has an average spacing of 3 half wavelengths in between. But basically we've averaged over all of these things, and so this is what we get. So the thing that happens over here, so this is the thing given by that formula, sort of our model of the delta function, so to speak. So we have a narrow lobe, narrow main lobe, and we have low side lobes over here. And so this is a good thing to have. The expression for the variance, if you actually plot that, so the formula that I had, no, it's correct. The actual formula that I had on the board there before, and I said we'll look at it later, here's the graph of it, and basically, and we would have figured this out from looking at the formula as well. But basically what this says is that when you have these random arrays, that the fact that the variance here drops at the main lobe says basically the main lobe in a random array is pretty stable. It's really pretty much unaffected by the distribution of the elements. And however, the side lobes, there's a tremendous amount of variation that goes on there. So the central lobe is something we don't have to worry about too much. So all the action's kind of in the side lobes. Now the previous expression here that we calculated and had the graph of, that was the expectation. That was the absolute value of the expectation of these random arrays. Now these things are complex valued in the side lobes, so there's a lot of cancellation that occurs. If we calculate instead the expectation of the absolute value of the side lobes, then of course we don't see all that cancellation, and then we see basically we get this graph over here. And so notice here that the side lobe level here is about square root of n. We have n many sensors, so n is 40. So here we are at about square root of n. So what this graph tells us is that in any particular random realization of an array, we would expect the side lobes basically to be bouncing around this level over here and have a main lobe that looks pretty much like that. And just to illustrate that, there's an actual particular random array for the elements, and we see precisely this pattern. So this, of course, is reality. This is what's really going to happen in an array. And what we would like to do is we would like to get these peaks down in the side lobe. So this becomes a mathematical question. How can we bring down all of these peaks? And ideally, we'd like to get them down to there, but that's probably not possible. So the question is, what can we do? Or in a random array, what's the behavior of these side lobes anyway? Well, I don't want to get into random arrays per se, because that's not the interest here. But one can actually prove a theorem that says essentially the side lobes, the order of the sup norm of the side lobes are essentially on the order of square root of n log n. And the thing that we don't want here is we don't want the log n here. We would like things to be O of log n. Okay, so what I would like to do here is, in terms of the structure of the talk, so that I don't run out of time or the bulb burns out or anything like that, let me give you kind of the punchline right now and then tell you sort of how we get to it. And hope I have enough time to actually do that. So here is the construction of a set of integers which has the right behavior. So the construction goes something like this. Fix some p, this is going to be our density factor, and pick an n, and we're going to end up constructing a subset of the interval of integers from 0 to p to the n power. And the subset we have here is going to have a density of about 1 over p. And so the way this construction works is you take an n tuple here of numbers from 0 to p minus 1. Here's another one here, and we consider these two operators here. So here's a reversal operator, just does that, and here's sort of a truncated right shift operator. So with these two operators, then if we take any integer k from 0 to p to the n minus 1, we can consider the base p expansion of that integer, and this gives us a collection of digits here, and that's what the vector omega here is supposed to represent. And then we're going to define a set in the following way. So given a p, given an n, given an arbitrary n tuple here, and given an arbitrary s here, these are going to be sort of some parameters that define a set. We are going to, for every integer in this interval, we are going to just look at this expression over here, where the brackets is the standard inner product. So we reverse the digits in here. We, for the digits from k, we do a truncated right shift. We take the inner product of the same expression, and if that is congruent to s mod p, then we say that integer k belongs to our set, otherwise the integer does not. So that defines a subset of our interval from 0 to p to the n. And it's a very easy subset to implement, obviously. Now, the reason this subset is a good subset is because of the following two theorems. The first theorem is that, so if we take, for this subset here, if we take this trigonometric polynomial here with frequencies in this subset here, call this h sub n s nu, then you can show that, that the magnitude of this is bounded by this expression plus that. Now this expression over here, again, notice that's our basic model delta function that we're interested in. And so this kind of then represents the error from that delta function thing. Now, this expression over here, this was not the magnet, this was not the thing that was at level square root of n, this was the thing that basically dropped off. And so the thing we really expect is, we really expect the difference from this and this to be on the order of square root of n. I mean, it's not, we wouldn't expect the difference between this and this to be less than epsilon or anything like that. Now, so we have this inequality here. The next theorem over here is it gives an estimate on the number of points that we have on the set that was constructed. And so the estimate looks like this. And because here we have this sort of this n over 2 term over here, that means asymptotically this thing is order of p to the n minus 1. And p to the n minus 1 is exactly 1/p of our entire large interval, which is of the length p to the n. So the density of our set is approximately 1 over p here. Okay? So we have a thin set over here, and because the number of because n here, so let's change the notation, just call the magnitude of this thing here, the cardinality of this thing here to be capital N. And so capital N we can think is essentially p to the n minus 1 here. This term over here then, this is essentially a square root of n term. And so there we have our result that we are O of square root of n. And in fact we have a constant here, which tells us a constant which is a p minus 1 constant. Now, so that's our conclusion here, that we get the thing which is O of square root of n. So mathematically, this is, for me at least, satisfying. From a strictly engineering perspective, though, in the purely random case, we had essentially, if you think of that square root of n as, quote, the constant multiplying, or the square root of log n part as multiplying square root of n, square root of log n as a number, of course, grows very slowly from a practical perspective. And so before you see, so when you compare that here to the p minus 1, you don't really start seeing the gains of this until n gets really pretty large. And many times engineers are not interested in arrays that are all that large. I mean, they don't want thousands and thousands and thousands of elements. So from a further research perspective, one would like to actually find other constructions which achieve a square root of n side lobes, but perhaps with a better constant here than this over here. In fact, it's a really interesting question to ask, what is really the best constant we can hope to achieve over here? That's unknown, what that might be. In any case, so this, wow, we have time already? Okay. This is going to be tough to try to explain where this comes from. Well, I've spent 25 minutes. In fact, I only have 4 minutes. Maybe I should just quit at this point rather than attempt to go into an actual explanation. Let me say one word, though, where this is coming from, since I mentioned extremal problems in the plural. So the other extremal problem to which this is related, and in fact this is the thing that really ends up yielding the solution that I mentioned over here, is what is known as the unimodular polynomial problem. And so here the situation is one has a polynomial, and the question is how close can we come to the situation where the modulus is constant for on both the transform side and the time side. And again, of course, that's impossible to do. And to be a little bit more specific, one might say, okay, well, suppose we set the coefficients all to have magnitude 1, just to nail it down. So that's the term unimodular, where that comes from. And in that particular case, then what we have, of course, is we have the L2 norm is equal to the square root of n. The sup norm is greater than the L2 norm. And if this actually occurred, if this actually was constant, then of course the sup norm and the L2 norm would be identical, and this inequality would be an equality. So, so asking how close can we get to this situation becomes sort of equivalent to saying, how close can this inequality be over here? This goes back to some early work of Littlewood, and in fact, there was a conjecture, Erdős made a conjecture basically saying that it's not possible for any unimodular polynomial to do better than having an absolute constant here that's greater than 1. And so that was the Erdős conjecture. And that conjecture was actually disproved in the 90s by J.P. Kahan in a rather remarkable paper where he showed not only can you get this within 1 plus epsilon of that, but in fact, you can even get the lower bound, even the minimum of this polynomial, can be within 1 minus epsilon of the square root of n. So he actually basically said that this quantity as a function of x here is within an epsilon band of square root of n. You can ask the same question then. So you can loosen things up, well, loosen or tighten, whichever. You can say, well, what about instead of unimodular polynomial complex numbers, how about simply plus and minus 1s? What can be done there? Well, that still remains an open question. Nobody knows whether one can get within 1 plus epsilon with that, or here's the minimum, what is it, and so forth. And Littlewood himself made some comments about this. He said that on some days he felt that yes, he could do it. On other days he felt no, he couldn't do it. And so that's kind of it. Okay, let me take maybe just a few more seconds, just at least give a tiny hint of where the solution comes from. So the key, well, so the plus and minus one case here, many of you, perhaps all of you out there in the audience, are familiar with the Rubin-Shapiro polynomials. In 1957, Harold Shapiro, I think in an MIT master's thesis here, came up with this collection of polynomials. Rubin published in the proceedings somewhat later exactly the same polynomials. And actually turned out later that Marcel Golay had an earlier paper called Multi-Slit Spectroscopy, which actually had the exact same thing in it, although not from a polynomial perspective, from a sort of optics perspective. And basically, this is a very simple recursion here. You simply start with a pair of polynomials 1 and 1, and you generate another set here with this recursion. So, for instance, here after the first step, one gets this. At the next step, one gets this. And expanding this out, you notice here that what we get here is we get, so the P2 and Q2 are degree 4, which is 2 to the 2 power. I know you're going to stand up here. Okay. In any case, the plus and minus 1's in it. Notice I'm ignoring it. Essentially, it's a generalization of all of this. Allow me, well, maybe I'll stop here. If one can generalize this rather drastically, this idea, and that's what ultimately led to the construction that I showed.